Hi all, today we are going to handle the topic the factors which are affecting the choice of specific loadings in DC machines. This is a very important topic. Before looking into the factors, we will first study about the estimation of armature power which is being developed in the DC machine. You are quite familiar with this power flow diagrams which you have studied in your electrical machines course. The first diagram represents the power flow in the case of generator, DC generator, and the second diagram is representing the power flow diagram in the case of DC motor. In the case of this generator, if you are subtracting this friction, windage and iron loss from the mechanical input, you will be able to obtain the armature power developed. You can obtain the value of armature power from the output power also. In order to obtain that, you have to add output power with the field copper loss and the armature copper loss. This PB is actually representing the losses which are occurring in the brushes. In motoring mode, if you are subtracting the field copper loss and armature copper loss from the input electrical power, you will be able to estimate the value of armature power developed. You can also estimate the value of armature power developed from the output mechanical power by adding friction windage loss and iron loss with the output mechanical power developed. The relation for armature power developed is also shown here. PA is equal to input power minus friction windage and iron loss. This is in the case of generator. Instead of input power, we can easily write it as output power divided by efficiency minus friction windage and iron loss. And the relation for motor is also shown here. This relations you don't have to by heart it. You just need to know the power flow diagram, then you will be able to write these relations from there. In the case of very large machines, this friction windage and iron losses are almost neglected. So these relations can be modified into this form. That is in the case of generator, PA is equal to P output by efficiency. Whereas in the case of motor, PA is equal to P output. That is the armature power developed is equal to output power in the case of motor. Whereas in the case of generator, the armature power developed will be same as that of the input power. This is possible. This relation is valid only in the case of large machines. Large machines are those which are having ratings which are greater than 250 kilowatts. Please note, large machines are those which are having power ratings greater than that of 250 kilowatts. After neglecting this friction, windage and iron losses from these two relations, we will be getting the simplified relation in this form. In the case of small machines, it's not possible to neglect the friction, windage and iron losses. In small machines of power ratings which are actually less than 250 kilowatts, these losses are considered to be 1/3 of the total losses. Total losses is determined by subtracting the output power from the input power. Input power can be written as P output by efficiency. Hence the total losses we will be getting it as P output into 1 minus efficiency divided by efficiency. From this we can write the relation for friction, windage and iron losses which is actually 1/3 of the total losses. We have seen in the power flow diagram of DC motor, the armature power developed is actually the sum of output power plus friction, windage and iron loss. So for this friction, windage and iron loss, make the substitution. And then simplifying it, we will be able to estimate the value of armature power as 1 plus 2 nu divided by 3 nu into output power. Similarly, in the case of generators of ratings which are actually less than 250 kilowatts, from the power flow diagram, we very well know that the armature power developed is actually the difference between input power and friction, windage and iron loss. For this friction, windage and iron loss, make the substitution. And instead of input power, we can write it as P output divided by efficiency. Then further simplifying it, we will be getting the relation as 2 plus efficiency divided by 3 into efficiency, the whole into output power developed. So these two are actually the relation for generator and motor in the case of small machines, whereas in the case of large machines, the relations are PA is equal to P output divided by efficiency and PA is equal to P output. All of you must remember these relations, then only you will be able to solve the problems associated with this. These relations are valid only for machines having ratings which are less than 250 kilowatts, and these relations are valid only for machines which are having ratings greater than that of 250 kilowatts. In problems associated with the design of DC machines, the very first step which you have to find is the armature power developed in the machine. So if you don't know these relations, then you won't be able to solve the problems further. In our last class, we have obtained the output equation of DC machine. In the output equation, we have derived the relation for armature power developed or power developed by armature as C0 d square L into small n. Determine the main dimensions in the case of DC machine, that is to find the values of D and L. From the output equation, we must know the value of armature power developed, C0 and small n. Then only we will be able to find the value of D and L from the output relation or the output equation. So for designing of a DC machine, the values of P output and efficiency must be given. Then only we will be able to find out the value of armature power developed. Then to get the value of D and L, we have to first calculate the value of C0. As you have studied in the last class, C0 is actually equal to pi square BAV AC into 10 raised to minus 3. From the relation of C0, it's very clear that C0 is actually having dependency on specific magnetic loading and specific electric loading. Therefore, it's very important to consider all those factors which will affect the values of specific electric loading as well as specific magnetic loading. First, we will see the factors which will affect the values of specific magnetic loading. Then we will move to those factors which are affecting the values of AC, that is specific electric loading. First, we will see how this flux density in teeth will affect the value of specific magnetic loading. Flux density in the teeth is given by the relation flux in each teeth divided by area of each teeth. Here you will be able to see the flux in each teeth is actually the flux over this slot pitch. Slot pitch is actually the center to center distance between these two slots. So the flux in this teeth portion is same as that of the flux over the slot pitch. Flux over the slot pitch can be easily found out by dividing the total flux in the air gap divided by the actual number of slots. From the relation of specific magnetic loading, that is B average is equal to P phi by pi dl, we can easily write P phi is equal to B average into pi dl. So making the substitution here, the relation becomes P average pi dl divided by S. In this relation, this pi d by S is indicating the slot pitch. So instead of pi d by S, we can make the substitution Ys. Hence the flux over this one slot pitch, which is actually the flux in each teeth, becomes P average into Ys into L. Make the substitution here. This area of teeth can be easily determined by multiplying this width of teeth with the length. Length will be actually the whole length of the armature. We have already studied this relation in the topic tooth MMF. You can refer that also. So in this relation, if you are seeing these two terms gets cancelled, and finally the relation becomes B average into Ys divided by Wt. So from this relation, it's very clear that the flux density in the teeth is having direct proportionality with the specific magnetic loading. So if you are choosing a very large value of specific magnetic loading, then definitely the flux density in the teeth also becomes a large value. This large value of flux density in teeth will increase the iron losses in the teeth. In order to produce this large value of flux density in teeth, the required MMF for the teeth also has to be large. This consequently will result in large copper loss in the field. In order to avoid all these unwanted effects due to this large value of specific magnetic loading, it will be ensured that the value of B average, that is a specific magnetic loading, will be fixed in such a way that the value of flux density in teeth, where the teeth section is minimum, will not exceed the value of 2.2 Weber per meter square. That is, you have to choose a particular value of specific magnetic loading in order to ensure that the value of Bt, where tooth section is minimum, will never exceed the value of 2.2 Weber per meter square. This will be the limiting parameter for specific magnetic loading considering the effect of flux density in teeth. Hope it's clear for you. I will be explaining it once again. If you see from this relation, it's very clear that the flux density in teeth is having direct proportionality with the specific magnetic loading. So if you are choosing a very large value of specific magnetic loading, then definitely the value of flux density in teeth also becomes large. From the relation of the iron loss, that is hysteresis loss and eddy current loss, we very well know that those two losses are having dependency on the value of flux density. So if this value of flux density is large, then definitely the magnitude of iron loss also will be very large, which is an undesirable effect. Moreover, to produce this large value of flux density in teeth, the MMF required for the teeth will be very large. In order to produce this large value of MMF, the magnitude of field current has to be large. This will further result in a large field copper loss, which is also an undesirable effect. So as to reduce this undesirable effects, a restraining parameter is set here. That is, if you are increasing the value of B average, you will be able to increase to a particular value so that the value of BT at the minimum section of teeth will not exceed the value of 2.2 Weber per meter square. Next parameter is frequency. As we know, when the armature of the DC machine is rotating, the armature alternately comes under the influence of both North Pole and South Pole. In one rotation of the armature, it faces P by 2, where P is actually the total number of poles. It faces P by 2 magnetic reversals. If the speed of the machine is n RPS, that is small n RPS, from the speed relation we can say that the armature will complete n revolutions in a second. So when the armature is rotating for n times in a single second, and during one rotation it is facing P by 2 magnetic reversals, then the number of magnetic reversals in a second can be said to be P by 2 into small n. That is actually the frequency of magnetic reversals. That relation is represented here. As you have studied in your machines course that the iron loss, which is actually the hysteresis loss, and eddy current loss is having a dependency over the frequency. So if you are choosing a very large value of frequency of magnetic reversals, then definitely the magnitude of iron loss will be also very high. Therefore, we must ensure that a large value of specific magnetic loading should not be used in the case of machines with large value of frequency of magnetic reversals. This is because if the value of B average is high, then definitely the value of BT will be high, and hence the iron losses over there will be very high. If you are trying to increase the value of frequency of magnetic reversal, this will consequently result in a very large value of iron loss, which is actually a unfavorable effect. So it must be ensured that if you are choosing a large value of B average, that is specific magnetic loading, then the frequency of magnetic reversals should be small one. Next factor which is affecting the value of B average, that is specific magnetic loading, is voltage rating of the machine. In the case of large voltage rated machines, that is high voltage rated machines, the amount of insulation which will be provided to the conductors will be quite large. In order to accommodate this large conductors, that is the conductors with large insulations, the width of the slots will be made large. This will consequently result in a narrower teeth. So we must make sure that for large voltage rated machines, the value of B average, that is specific magnetic loading chosen, must be a small one. Otherwise, if you are choosing a large value of specific magnetic loading, this will result in a large value of BT beyond the permissible limits as the area of teeth are narrower. The last parameter which will be affecting the specific magnetic loading is size of the machine. If the size of the machine is quite large, size of the machine is large means the diameter of the machine will be definitely large. As the diameter of the machine is quite large, then definitely the width of teeth will be also larger. The teeth won't be narrower. This will allow to choose a very large value of B average, that is specific magnetic loading. This is actually a graph which is depicting the value of specific magnetic loading along y-axis and the value of armature diameter. So you can see very clearly from this graph, as the value of armature diameter is increasing, the value of specific magnetic loading also goes on increasing. So it's very clear that if you are choosing a larger size machine, then definitely the value of B average can be also selected to be a large value. In this case, the value of BT won't go beyond the permissible limit. So considering all these factors, the range of B average, that is specific magnetic loading, will vary from 0.4 to zero point 0.8 Weber per meter square. Next, we are going to see the advantages and disadvantages of choosing a large value for specific magnetic loading. If you are choosing a large value for specific magnetic loading, that is, if you are choosing a large value for B average, then definitely the value of C0 will be very large. As you know from the output equation, the relation for armature power developed is C0 d square L into small n. So if the value of C0 is large, then definitely the value of d square L, which is actually indicating the volume, means equivalent volume of the DC machine. So if you are choosing a large value of C0 for a particular armature power developed, then definitely you will be able to reduce the value of d square L, that is the size of the machine. So that is the very first advantage, that is size and volume of the machine is reduced. Due to this, the weight of the machine also can be reduced and the overall cost of the machine also can be reduced. The major disadvantages we have already mentioned for large value of B average is, if you are choosing a large value of B average, then the value of BT will be large, which will result in large value of iron losses. If the value of BT is large, then the field MMF has to be increased. So definitely the field copper losses also will increase. Tooth flux density increases, higher magnitude of no load current, as the value of field MMF has been increased. There occurs some noise in the machine, and there is a possibility of magnetic saturation in iron parts, specifically in the tooth portion of the DC machine. These are the disadvantages for choosing a large value for B average. Next, we are going to study the factors which are affecting the value of specific electric loading, which is usually represented as small AC. The first factor is temperature rise. If you are choosing a large value for AC, all of you know the relation for AC is actually Iz into Z divided by pi d. So if the value of AC is large, it clearly indicates that the large value of current will be flowing through the conductors, which will result in large losses. Consequently, large temperature rise also occurs. So a large value of AC can be chosen, or it must be chosen only for those materials which are having proper insulation to withstand this high temperature rise. Next factor is speed of the machine. If the speed of the machine is quite large, then definitely it will be having a good ventilation system. So for large speed machines, due to this better ventilation property, you can definitely choose a large value of specific electric loading, that is AC. Next factor is voltage. Just like we mentioned before, for large voltage rated machines, a large value of insulation will be required, or the insulation requirement is also quite large. So due to this large insulation which is being provided for large voltage rated machines, the space which is available to accommodate the number of conductors will be definitely quite small. So for large voltage rated machine, only very few number of conductors can be accommodated in the slot. So due to this, in the case of large voltage rated machine, the value of AC to be chosen must be small. Next factor is armature reaction. You have also studied this in your machines course. Armature reaction is actually defined as the effect of armature flux on main flux. If you are choosing a large value of AC, then definitely the value of armature MMF, that is the armature flux, also will be quite large. This will distort the main flux by cross-magnetization and demagnetization. In order to prevent this, the field MMF has to be increased, which will result in large cost of the conductors. Next factor which is affecting the value of specific electric loading is commutation. Commutation is actually when a conductor which is under the influence of north pole is moving towards the south pole, then definitely the direction of current in the conductor has to be reversed. This is said to be the commutation. If you are choosing a very large value of AC, there are two ways you can choose a large value for AC. In one way, you can increase the value of Z at the numerator, and the other way you can decrease the value of D at the denominator. If the value of Z is large, then naturally the number of coils will be also quite large. So in that particular case, the value of inductance will be large, because in the relation for inductance, you have studied this in your 11th and 12th standard. This is the relation for inductance. Inductance is actually directly proportional to square of the number of turns. So if the value of Z is large, there is a number of conductors, then definitely the number of turns will be also very large. This will consequently result in a large value of inductance. That is, this high value of AC will result in large value of inductance. If a large value of AC is opted by reducing the value of armature diameter, then it's very clear that the wider slots cannot be used because the diameter of the armature is small in size. So the only way which is available to accommodate all these conductors is by providing a deeper slot. If the depth of the slot is increased, this also will result in a large value of inductance of the armature. So in both cases, that is, if you are increasing the value of AC by increasing the number of conductors or by decreasing the value of diameter, in both these cases it will result in a large value of inductance of the armature. You have studied in your machines course that whenever a conductor is moving from the influence of north pole to south pole, the direction of current in the conductor will get reversed. That is, if the conductor is under the influence of north pole, and if the current which is flowing through the conductor is I, if the same conductor is coming under the influence of south pole, the direction of current will get reversed. So the current which will be flowing through that conductor will be said to be minus I. Due to the inductance present in the coil, definitely an EMF will get induced in this coil due to the reversal of this current, and that particular EMF is said to be L into di by dt. Here the change in current is actually 2I, because the current is changing from plus I to minus I. So the relation for induced EMF can be said to be L into 2I by dt. This induced EMF is said to be the reactance voltage. So if the value of inductance is quite large, then definitely the magnitude of reactance voltage also will be large. According to Lenz's law, the direction of induced EMF is such as to oppose the cause that produces it. In the case of this induced EMF, the cause is actually the change of current when the conductor is moving from north pole to south pole. So this reactance voltage will oppose this change of current. That is, it won't permit the current to change from plus I to minus I according to the Lenz's law. So definitely the commutation won't occur properly. It will lead to the phenomena of delayed commutation, which will further worsen the commutation conditions in the machine. So it's clear that the value of AC must be taken in such a way that it should not harm the commutation conditions of the machine. If you are choosing a very large value of AC, the large value of AC can occur either due to the large value of Z or due to the small value of D. In both these cases, the magnitude of reactance voltage will increase. This will result in delayed commutation, which is not a desirable effect. Considering all these parameters, the value of AC ranges from 15,000 to 50,000 ampere conductors per meter. You must remember the range of AC and the range of specific magnetic loading. Next, we are going to see the advantages and disadvantages of higher specific electric loading. The advantages remains the same as that of the case of advantages of higher specific magnetic loading. Disadvantages: if you are choosing a large value of AC, definitely the copper losses will be large. Commutations becomes poor. Commutation reactance voltage will get increased. Field copper loss also increases. And overall temperature rise will be high. This is a very important topic. I have seen questions related with this in almost all the previous year university question papers. So please understand the concept thoroughly and study it. In the next class, we will study the overall dimensions of DC machine and numerical problems associated with it. Thank you.